Imagine you are standing on the surface of Earth looking up. You know the planets are out there. You have seen the diagrams, the neat rings of orbit, each one farther than the last, arranged like lines on a target. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. And then nothing. The edge. Clean. Defined. Understood. That diagram is wrong. Not slightly wrong. Not a simplification for school children. Fundamentally, structurally, cosmically wrong. The solar system does not end where those diagrams stop. It does not end at Neptune. It does not end at Pluto. It does not end anywhere you have been taught to expect. The true boundary of our solar system lies so far beyond those familiar worlds that the distance itself becomes nearly impossible to hold inside a human mind. To understand what the edge actually is, you first have to forget everything the diagram told you. In 1977, humanity launched two small probes into the darkness, Voyager 1 and Voyager 2. Both spacecraft were sent outward on trajectories that would carry them past the giant planets and into the deep unknown. They have been traveling ever since. For nearly 5 decades, those two probes have moved without pause, without rest, without a single moment of deceleration. They are the fastest human-made objects ever sent into space. And as of today, they are still inside the solar system. Let that settle. 47 years of continuous travel, speeds that would cross the United States in under 4 minutes. And still inside, still within the gravitational and energetic reach of our sun. That single fact dismantles every intuitive model most people carry. Distance, it turns out, is the true antagonist of this story. Not darkness, not cold. Distance. The kind of distance that defeats imagination before it even begins. Begin at the beginning. A spacecraft leaves Earth orbit and starts moving outward. Within minutes, the moon passes in the rear view. Within hours, the inner solar system begins to shrink. Mars takes several months to reach. Already the sun behind you is smaller than you expect. Already the warmth has faded to a cold, distant glow. But you are nowhere near the edge. You have barely started. The asteroid belt comes next, a ring of rocky debris orbiting between Mars and Jupiter. When people hear the word belt, they imagine something dense, a wall of tumbling rock. Science fiction has trained that instinct deep. In reality, the asteroid belt is almost entirely empty space. Individual rocks separated by hundreds of thousands of kilometers. A spacecraft passes through without incident. There is no gate here, no edge. Just scattered remnants of a planet that never finished forming, drifting in silence as you push onward. Jupiter rises ahead. Vast, striped, violent. The largest planet in the solar system, large enough to swallow every other planet combined and still have room. Its gravity bends the trajectory of every object that passes near it. The Voyager probes used Jupiter as a slingshot, borrowing its momentum to accelerate deeper into the outer system. Past Jupiter, the sun has already shrunk to a bright star. Not a disk. A point of light. Intensely bright, yes, but a point. And still you are not close to any edge. Saturn, then Uranus, then Neptune. Each one farther than the last by an almost geometrically expanding margin. Neptune orbits the sun at roughly 4.5 billion kilometers from Earth. When Voyager 2 reached Neptune in 1989, after 12 years of travel, mission controllers in California had to wait over 4 hours for a signal, traveling at the speed of light to make the round trip. 4 hours at the speed of light. And Neptune is considered the outermost major planet. This is where most people place the edge. Neptune. Or perhaps they extend it slightly to include Pluto, that small, complicated world reclassified as a dwarf planet in 2006. Pluto feels like a boundary. It has the psychology of a boundary. The last named world. The last object most people can point to on a map. When the New Horizons probe flew past Pluto in 2015 and sent back those first detailed images, the heart-shaped nitrogen ice plain, the mountains of frozen water ice, it felt like a final destination, a farewell photograph at the edge of the known. But that's not the real problem. Pluto is not at the edge. Pluto is not even close to the edge. Pluto orbits within a structure so vast that Pluto itself feels as close to Earth as a neighborhood, relative to what lies beyond. Past Neptune, beginning at around 30 astronomical units from the Sun, and extending to somewhere around 50, lies the Kuiper Belt. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. The Kuiper Belt spans from 30 to 50 of those units. It is a ring of frozen objects, dwarf planets, and ancient debris circling the outer solar system. Pluto lives here. So does Eris. So do hundreds of thousands of smaller bodies, most of them unnamed, most of them never observed directly. The Kuiper Belt is not a wall. It is not a fence. It is a vast, diffuse field of primordial material, the frozen leftovers of solar system formation, orbiting in a cold they have never escaped. The Kuiper Belt feels like it should be the edge. It has mass. It has structure. It marks a clear transition from the planetary zone to something else entirely. For a long time, astronomers treated it as an outer border. But science, like space itself, does not permit comfortable endings. It gets worse. Beyond the Kuiper Belt, extending far past 50 astronomical units, the Sun's influence does not simply stop. It fades, it weakens, it wars with something else. The Sun constantly releases a stream of charged particles with the solar wind, radiating outward in every direction at hundreds of kilometers per second. This wind fills the inner solar system, presses against planetary atmospheres, shapes magnetic fields, and pushes steadily into deep space. But eventually it loses. Eventually the interstellar medium, the thin gas and dust that fills the space between star systems, pushes back hard enough that the solar wind slows, compresses, and stalls. The region where this battle is fought has a name. The heliosphere. It is a massive bubble of solar influence surrounding the Sun and all the planets, stretching out to roughly 100 astronomical units in the direction facing into the galaxy's oncoming wind, and much farther to perhaps 300 astronomical units or more in the trailing direction, forming a comet-like tail of solar material dragged behind the Sun as it moves through the galaxy. The outer boundary of the heliosphere, the heliopause, is where solar wind pressure finally equals interstellar pressure, where the Sun's breath finally stops. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed it in 2018. Both probes are now, technically, in interstellar space. Scientists announced this milestone with careful, restrained language. The probes had entered a new domain, a region where the Sun's particles no longer dominate, a region where the raw material of the galaxy itself presses inward. And this changes everything, because the heliopause is still not the edge of the solar system. The Sun's gravity extends far beyond the heliopause. Gravity does not stop at a boundary of particles. Gravity reaches and reaches and reaches, orbiting in the extreme cold and darkness well beyond the heliopause, perhaps beginning at 2,000 astronomical units and extending to 100,000 or more, lies a theoretical structure astronomers call the Oort Cloud. A vast spherical shell of frozen comets and icy bodies gravitationally bound to the Sun, drifting in slow, distant orbits at the outermost limit of solar gravity's reach. The Oort Cloud has never been directly observed. It is inferred, calculated, deduced from the paths of long-period comets that occasionally fall inward toward the Sun after being disturbed by a passing star or the gravitational tide of the galaxy itself. The Oort Cloud, if it exists as modeled, extends nearly a quarter of the distance to the nearest star. Proxima Centauri, our closest stellar neighbor, sits at roughly 268,000 astronomical units from Earth. The outer Oort Cloud may reach 100,000 astronomical units or more. The solar system's gravitational reach and the space between stars are not cleanly separated. They overlap. They blur into each other across distances so enormous that the concept of a defined border begins to dissolve. No spacecraft has ever entered the Oort Cloud. At Voyager's speed, reaching it would take tens of thousands of years. Crossing it entirely would take longer than the age of modern human civilization multiplied many times over. It is a frontier that exists beyond the reach of any mission humanity can currently imagine, governed by forces operating across timescales that dwarf recorded history. And yet it belongs to our solar system. Ours. The Sun's domain. The edge of the place we call home. The solar system does not end where the planets stop. For most of the 20th century, Pluto meant something. It meant the edge. The final world. The last outpost of something organized and named before the solar system dissolved into empty dark. School children memorized it. Textbooks printed it. The public held it with the particular affection reserved for the smallest, most distant, most vulnerable member of any group. And then, in 2006, the International Astronomical Union reclassified it, stripped it of its planetary status, reduced it, in the language of official science, to a dwarf planet. The backlash was immediate and emotional. People grieved Pluto's demotion as though something had been taken from them. They were looking at the wrong event entirely. Pluto was not diminished in 2006. It was finally understood. The reclassification was not a demotion. It was a revelation. Because the reason Pluto lost its planetary title was not that it was too small or too cold or too far. It was that scientists had realized Pluto was not alone. It was the first recognized member of an enormous population of frozen worlds occupying the outer solar system. A population so vast, so ancient, and so scientifically significant that it fundamentally rewrites the story of how this solar system formed and what it actually contains. Beyond Neptune, the solar system does not fade into emptiness. It fills with something else entirely. The Kuiper Belt begins at roughly 30 astronomical units from the Sun, just beyond Neptune's orbit, and extends outward to approximately 50 astronomical units. That is a band of space spanning hundreds of millions of kilometers in width, wrapping completely around the solar system in a thick, diffuse ring. Within that ring orbit hundreds of thousands of objects, possibly millions, most of them too small and too faint to have been individually cataloged. Most of them frozen, most of them ancient beyond easy comprehension. These objects are not debris in any casual sense. They are relics. They are the preserved remnants of the material from which the solar system itself assembled, frozen in place before gravity ever gathered them into a planet, waiting in cold storage for a civilization curious enough to find them. Pluto is among the largest of these objects. It has a diameter of roughly 2,377 kilometers, smaller than Earth's moon, but large enough to have a layered atmosphere, a geologically active surface, and at least 5 known moons. Its largest moon, Charon, is so proportionally massive relative to Pluto itself that the two objects orbit a common center of gravity located outside Pluto's surface. They do not orbit each other in the conventional sense. They face each other permanently, tidally locked, rotating in slow synchrony across a distance of less than 20,000 kilometers, like two dancers holding each other at arm's length as they spin through the dark. When the New Horizons spacecraft flew past Pluto in July 2015, it sent back images that shocked even the scientists who built it. The surface was not the uniform, cratered, geologically dead world they expected. There were mountains of water ice rising 3 kilometers above the surrounding terrain. There were plains of nitrogen ice so young in geological terms that almost no impact craters had formed on them, meaning the surface was actively refreshing itself through a process still not fully understood. There was a vast heart-shaped basin, later named Tombaugh Regio, visible even in the first long-range images, as though the planet itself had something to say. Pluto was alive in ways nobody anticipated, but the more unsettling realization was not what Pluto looked like. It was what Pluto represented. It gets worse. In 2005, astronomer Mike Brown and his team discovered a Kuiper Belt object they initially thought might be larger than Pluto. They named it Eris. When measured, Eris turned out to be almost exactly Pluto's size, but roughly 27% more massive. Denser, heavier, more reflective. Eris orbits far beyond the main Kuiper Belt on a highly elliptical path that carries it out to nearly 98 astronomical units from the Sun at its farthest point. It has a small moon named Dysnomia. It sits in near-complete darkness at temperatures approaching negative 230 degrees Celsius. And it is, by every reasonable measure, every bit as complex and real as Pluto. Eris was not alone in arriving. The same era of sky surveys that found Eris also found Makemake, a reddish methane ice-covered dwarf planet with no detected atmosphere at its farthest orbital distances, appearing to shed its air as pressure drops during the longest winter portions of its 310-year orbit around the Sun. It found Haumea, one of the strangest objects in the outer solar system, spinning so rapidly that a day on its surface lasts only 4 Earth hours, and that rotational speed has stretched it into an elongated ellipsoid shape, longer than it is wide, tumbling through space like a cosmic rugby ball. Haumea has 2 moons and a faint ring, discovered as recently as 2017. And these are only the objects large enough to be classified. Behind them, stretching across the full width of the Kuiper Belt, orbit hundreds of thousands of smaller bodies. Frozen, dark, ancient, mostly unnamed. Astronomers estimate that the Kuiper Belt contains at least 100,000 objects larger than 100 kilometers in diameter. The actual population of smaller objects likely runs into the tens of millions. Most have never been individually observed. Most never will be with current technology. They drift in silence, completing their long, slow orbits while the sun burns at a distance so great it provides less warmth than a full moon does on a clear Earth night. But that's not the real problem. The question that haunts Kuiper Belt science is not merely how many objects exist out there. It is how they ended up there in the first place. And the answer to that question dismantles a second assumption. The idea that the solar system formed in the calm, orderly, concentric arrangement the diagrams suggest. The early solar system was violent. In the first hundreds of millions of years after the sun ignited, the giant planets were not in their current positions. Jupiter, Saturn, Uranus, and Neptune migrated. Their orbits shifted as they exchanged gravitational energy with the disk of material surrounding the young sun. This planetary migration, the movement of worlds each larger than anything in the inner solar system, sent gravitational shockwaves through every region the giants passed through or approached. Entire populations of smaller objects were flung outward. Some were ejected from the solar system entirely. Others were pushed into the distant, stable orbits they occupy today in the Kuiper Belt and beyond. The frozen relics of the outer solar system are not where they formed. They are where chaos deposited them. Each one carries in its orbit a record of violence so ancient that the planets responsible for it have long since settled into the quiet arrangements we now observe. Understanding this history changes the Kuiper Belt from a curiosity into a laboratory. These frozen objects preserve chemical and physical conditions from the earliest moments of solar system formation. Their surfaces record the composition of the original protoplanetary disk, the raw material from which everything, including Earth, assembled itself. When comets fall inward toward the sun from the Kuiper Belt, they carry that ancient chemistry with them. Some researchers argue that Kuiper Belt comets delivered significant quantities of water and organic molecules to the early Earth. If that hypothesis holds, the frozen worlds drifting silently beyond Neptune are not just relics of the solar system's past. They may be part of the origin story of life itself. And this changes everything, because the Kuiper Belt may not have fully revealed itself yet. Beyond its known population, theoretical models of solar system formation predict that additional large objects may still be waiting in the outer dark. Some astronomers examining the clustered orbital patterns of distant Kuiper Belt objects have argued that the gravitational signatures they observe are consistent with an undiscovered planet, a large, cold world, perhaps several times Earth's mass, orbiting at hundreds of astronomical units from the Sun on a path so wide that one complete orbit would take thousands of years. They call it Planet 9. It has not been found. It has not been confirmed. The debate among researchers continues, but the mathematical signal persists. Something out there possibly is shepherding these frozen populations in ways the known planets cannot explain. Every generation of astronomers has believed they understood the broad architecture of the outer solar system. Every generation has been shown they were missing something. The asteroid belt was mapped. Then the Kuiper Belt was found. Pluto was defined as the edge. Then Eris appeared. The planetary count stabilized at 8. Then the orbital anomalies emerged. The frontier does not cooperate with finality. Each discovery in the outer solar system has followed the same pattern. A boundary is drawn, and then something appears beyond it. The Kuiper Belt is not an ending. It is the first chapter of a much longer story about what occupies the dark between us and the stars. A story written in ice, preserved across billions of years and still being read. The solar system's outskirts are crowded with forgotten worlds. The sun is not quiet. It never has been. Every second from every point on its surface, the sun releases a continuous stream of charged particles, electrons, protons, helium nuclei, moving outward at speeds between 400 and 800 kilometers per second. This is not an occasional event, not a storm, not a seasonal emission. It is constant, relentless, a perpetual outpouring of energetic matter that has been flowing since the sun ignited roughly 4.6 billion years ago. It moves through the inner solar system, pressing against planetary magnetospheres, sculpting the tails of comets, stripping atmosphere from unprotected worlds. It reaches Earth and deflects around the magnetic field, funneling into the polar regions where it lights the sky in curtains of green and red. Then it keeps moving, past Mars, past Jupiter, past Saturn and the ice giants, past the Kuiper Belt and every frozen world within it. It does not weaken gradually and then stop. It travels, and then it hits something. That collision defines a boundary no human eye can see, no spacecraft can photograph, and no instrument can observe from Earth's surface. It is a boundary written in pressure. In the contest between the sun's outward breath and the ancient cold resistance of interstellar space. Understanding where the sun ends means understanding that contest, how it begins, how it escalates, and what survives on the other side. The stream of particles the sun emits has a name: solar wind. The name is deceptive in its simplicity because the solar wind is nothing like wind in any earthly sense. It carries no air, it makes no sound, it cannot be felt or heard. What it carries is a magnetic field, the sun's own magnetic field, stretched and dragged outward by the moving particles, extending into space like an invisible web of force wrapped around the entire solar system. This magnetic field, woven into the solar wind and propagating outward with it, forms a structure so large that it encloses every planet, every moon, every asteroid, every Kuiper Belt object, and everything else gravitationally bound to the sun. Astronomers call this structure the heliosphere. The heliosphere is the sun's atmosphere. Not the corona, which is the hot plasma visible during solar eclipses extending a few solar radii into space. Not the chromosphere or the photosphere. This is something far larger, a bubble of solar influence stretching tens of billions of kilometers in every direction, defined not by heat or light, but by the reach of the solar wind and the magnetic field it carries. Within the heliosphere, the particle environment is dominated by the sun. Solar wind fills the space between the planets. Solar magnetic field lines thread through the void. The sun's energetic output is everywhere, inescapable, defining the electromagnetic character of every cubic kilometer of space from Mercury's orbit outward. But the heliosphere is not infinite. The solar wind, fast as it is, does not travel forever without resistance. The interstellar medium, the thin gas, dust, and magnetic field that occupies the space between star systems, presses back. It is not empty. It is not a vacuum in any absolute sense. It carries its own pressure, its own particle density, its own ancient magnetic architecture inherited from the galaxy itself. And as the solar wind moves outward, it weakens, spreads, thins. Its particle density drops as it distributes itself across an ever-growing sphere of space. Eventually, at some distance from the sun, its outward pressure drops to the point where the interstellar medium can hold it back. What happens at that point is not a gentle handoff. It is a shockwave. The first boundary the solar wind encounters on its outward journey is called the termination shock. The name is precise. This is where the solar wind, having traveled from the sun at supersonic speeds, supersonic relative to the local interstellar medium, abruptly slows down. Not gradually, abruptly. The way a river of fast-moving water slows and thickens when it strikes a surface, spreading outward and losing its directional velocity in turbulence. The solar wind hits the termination shock, and its speed drops from several hundred kilometers per second to something far slower. The particles compress. The magnetic field intensifies locally. The smooth, organized outward flow of the solar wind becomes something chaotic and hot and strange. The termination shock is located at roughly 75 to 100 astronomical units from the Sun in most directions. Though its position varies depending on the Sun's activity level and the direction relative to the solar system's motion through the galaxy. In the direction the solar system faces as it moves through the Milky Way, the interstellar medium presses harder and the boundary sits closer. In the trailing direction, it extends farther, dragged outward by the solar system's momentum like the wake behind a moving ship. Voyager 1 crossed the termination shock in 2004. Voyager 2 crossed it in 2007. Both spacecraft were equipped with instruments designed to detect exactly this kind of transition, and both registered the crossing clearly. A change in particle density, magnetic field strength, and plasma temperature consistent with passing through a shock wave boundary. Scientists had predicted the termination shock would exist for decades before either probe reached it. The predictions proved correct. But correctness is not the same as preparation. Because what lies beyond the termination shock was stranger than the models suggested. It gets worse. Beyond the termination shock, the solar wind does not immediately surrender to interstellar space. Instead, it enters a transitional region, like a turbulent, uncertain zone called the heliosheath. Within the heliosheath, the slowed solar wind continues moving outward, but now it is compressed, heated, and chaotic. It no longer flows smoothly, it churns. The magnetic field lines, once ordered and spiral-shaped from the Sun's rotation, become tangled and irregular. The boundary between what belongs to the Sun and what belongs to the galaxy starts to lose its definition. Both Voyager probes spent years inside the heliosheath after crossing the termination shock, and the data they returned was not what researchers expected. One of the surprises was the detection of energetic particles flowing inward from outside the heliosphere. Cosmic rays from distant sources, filtering through the heliosheath in ways and quantities the models had not anticipated. The heliosphere, it turned out, was not as opaque a shield as assumed. The galaxy was leaking in, not overwhelming the solar environment, not suddenly replacing it, but present, detectable. A reminder that the boundary is not a wall, but a membrane, permeable in both directions, allowing an exchange of particles and energy between the Sun's domain and the surrounding cosmos. The outer boundary of the heliosheath is where the Sun's atmosphere finally meets interstellar space on equal terms. This boundary is the heliopause. The pressure from the solar wind, even slowed, even compressed, finally equals the pressure from the interstellar medium at the heliopause. Past this line, the Sun's particles no longer dominate. The particle environment becomes interstellar in character. The magnetic field becomes interstellar in origin. The chemistry and composition of space itself shifts. It is by the most physically meaningful definition available to science, the edge of what the Sun directly controls. The heliopause sits at roughly 120 astronomical units from the Sun, in the direction the solar system faces into its galactic orbit, and significantly farther in the trailing direction. Voyager 1 crossed it in August 2012. The instruments recorded the transition in unmistakable terms. a sharp drop in solar wind particle density, a simultaneous rise in galactic cosmic ray intensity, a change in the magnetic field direction, consistent with transitioning from solar to interstellar field lines. Scientists analyzed the data for months before formally announcing the crossing. They were careful. The data was clear, but the interpretation required certainty. When the announcement came, it was stated without ceremony. Voyager 1 had entered interstellar space. And this changes everything, because the data Voyager 1 and Voyager 2 have returned from beyond the heliopause reveals something the models did not predict. The transition was sharper than expected. The heliopause appears to be a relatively thin boundary, not a diffuse, gradual mixing zone, but something closer to a defined interface. On one side, solar wind particles. On the other, interstellar plasma. The change is measurable across a surprisingly narrow distance. The Sun ends more abruptly than science had assumed, but the shape of the heliosphere itself remains an active area of research and disagreement. For decades, the standard model described the heliosphere as comet-shaped, a blunt leading face pressing into the interstellar medium, and a long tail called the heliotail trailing behind. More recent data has challenged that picture. Some analyses of particle observations suggest the heliosphere may be more spherical than elongated. Others propose it has a crescent-like form and cross-section, shaped by the specific geometry of the surrounding interstellar magnetic field. No consensus has settled. The shape of the Sun's own atmosphere remains in 2024 a genuinely open question, because no single spacecraft has ever observed it from the outside. No mission exists to fly far enough, fast enough, to look back and photograph the heliosphere from a distance. The only measurements available are those taken by spacecraft passing through it from the inside. Scientists reconstruct its shape the way early explorers mapped coastlines, one data point at a time, piecing together a picture of something too large to be seen whole. What the heliosphere means beyond its geometry is this: the Sun does not simply exist as a point of light and gravity in space. It occupies space. It modifies space. It pushes the galaxy back across a volume so enormous that every planet, every moon, every ocean that has ever existed on any world in this solar system lives inside the Sun's own extended body. The solar system is, in this sense, a structure defined not by gravity alone, but by this vast, invisible atmospheric bubble, ancient, dynamic, and in constant tension with the galaxy surrounding it. The Sun carries its own atmosphere into interstellar space. Somewhere in the dark between the stars, a machine the size of a small car is moving away from you. It has been moving away from you since before most people alive today were born. It carries no fuel for propulsion, no engine fires to push it forward. It simply moves as objects in space move when nothing stops them, following the trajectory it was given nearly 5 decades ago with a precision that still functions today. It has no crew, no passengers. No living thing of any kind exists aboard it. What it carries instead is a set of scientific instruments, a failing power source, a fragile antenna pointed back toward a star it left long ago, and a golden disk containing the voices, music, images, and mathematics of a civilization it was built by. A civilization it will never return to. This is Voyager 1, the most distant human-made object in the history of our species, and it is still transmitting. To understand what that means, you first have to understand what was asked of it. In the late 1970s, NASA engineers recognized that a rare alignment of the outer planets, an alignment that occurs only once every 176 years, would allow a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in sequence, using each planet's gravity to accelerate toward the next. The window for this alignment opened in 1977. The Voyager program was built to meet it. 2 spacecraft launched 16 days apart in August and September of 1977, sent outward on trajectories calculated to exploit that planetary geometry before it closed. The engineers who designed the mission knew the probes might continue functioning long after their primary objectives were complete. They gave them enough power to potentially last decades. They did not know exactly how long. Nobody could have predicted what that decision would eventually mean. Voyager 1 reached Jupiter in March 1979. The images it returned redefined the planet. Before Voyager, Jupiter was a striped disk in a telescope. After Voyager, it was a world. The Great Red Spot resolved into a storm system, large enough to swallow Earth twice over, rotating with visible structure and internal turbulence. The moons revealed themselves as individual worlds rather than points of light. Io, the innermost large moon, showed something no one had anticipated: active volcanoes. Erupting, sulfurous, geologically violent volcanoes on a moon 628 million kilometers from Earth. The discovery arrived in the data and sat unrecognized for hours before a team member noticed a smudge at the edge of an image that turned out to be a plume of material rising hundreds of kilometers above the surface. Io was erupting as the spacecraft watched. Nothing like it had been seen beyond Earth. Saturn followed in November 1980. The rings viewed at close range and in full resolution for the first time were not the 2 or 3 broad bands visible from Earth. They were thousands. Thousands of individual ringlets, gaps, waves, and structures, some of them gravitationally sculpted by shepherd moons moving within the ring system, some of them still unexplained by any model available at the time. Saturn's moon Titan revealed an atmosphere thicker than Earth's, a dense orange haze of nitrogen and organic chemistry that hid its surface completely from Voyager's cameras. Scientists understood from those measurements alone that Titan was a different kind of world. Complex, chemical, worth returning to. After Saturn, Voyager 1's trajectory was bent deliberately away from the plane of the solar system. It would make no more planetary flybys. Its mission, in the classical sense, was functionally complete. But it did not stop. It kept moving, climbing away from the ecliptic at a steep angle, heading into the upper reaches of the outer solar system, on a course that would eventually carry it out of the heliosphere entirely. Voyager 2 took a different path. It continued to Uranus, arriving in January 1986, and then to Neptune in August 1989. At Neptune, it photographed a storm system called the Great Dark Spot, later found to have dissipated by the time the Hubble Space Telescope looked for it years later. It imaged Triton, Neptune's largest moon, a captured Kuiper Belt object orbiting backward relative to its planet's rotation, with geysers of nitrogen gas erupting from its surface through a process driven by sunlight so dim it barely registers on any instrument calibrated for the inner solar system. Voyager 2 returned the only close-range images of Uranus and Neptune that humanity has ever obtained. No mission has returned to either planet since. Both probes then moved outward into the deep dark, their planetary science complete, their instruments still watching, their antennas still turning toward the sun. But that's not the real problem. The problem is time. From the moment of launch, the Voyager probes have been running on a finite source of power. Each carries 3 radioisotope thermoelectric generators, devices that convert heat from the decay of plutonium-238 into electricity. At launch, each generator produced roughly 470 watts of power, enough to run a modest household appliance. Over the decades, as the plutonium decays and the thermocouples degrade, that output drops by approximately 4 watts per year. By 2024, each probe operates on fewer than 50 watts of electrical power. That is less than the energy used by a standard incandescent light bulb. To manage the decline, NASA engineers have been systematically shutting down systems. Heaters first, then redundant subsystems, then scientific instruments one by one as power becomes insufficient to run them simultaneously. Each instrument shut down is a small, permanent loss. A sensor that spent decades measuring the particle environment of the outer solar system goes dark. The data stream narrows. What remains is precious precisely because it is diminishing. Scientists prioritize the instruments that return the most critical data on the interstellar environment. But the choices are difficult, and the math is unforgiving. The probes are dying slowly, in the way that everything powered by decay must eventually die. In August 2012, Voyager 1 crossed the heliopause and entered interstellar space. The instruments registered the transition. Solar wind particle density dropped sharply. Galactic cosmic ray intensity rose. The magnetic field shifted. The crossing took place at roughly 121 astronomical units from the Sun, about 18 billion kilometers. The signal confirming the crossing, traveling at the speed of light, took more than 17 hours to reach Earth. Engineers and scientists gathered around monitors and waited for data that had already happened. That was already history by the time they received it. Voyager 2 followed in November 2018, crossing at approximately 119 astronomical units in a different direction, giving scientists 2 simultaneous measurement points in interstellar space for the first time. And this changes everything. Because the data those probes return from beyond the heliopause cannot be replicated by any other means. Earth-based observatories cannot directly sample the interstellar medium outside the solar system. The heliosphere itself blocks and modifies the particle and field environment that would otherwise reach the inner solar system. Voyager 1 and Voyager 2 are the only instruments humanity has ever placed in interstellar space. Every measurement they return is irreplaceable. Every data packet that arrives at the Deep Space Network's giant antennas in California, Spain, and Australia represents information that does not exist anywhere else and cannot be gathered again once those antennas fall silent. The signal itself is extraordinary in its fragility. At Voyager 1's current distance, a transmission sent at the full power of a 23-watt radio transmitter, roughly the power of a refrigerator light, arrives at Earth as a signal so faint it could only be detected by some of the most sensitive radio antennas ever built. The signal takes more than 22 hours to make the crossing one way. A round-trip communication, a command sent, a response received, takes more than 44 hours. The spacecraft cannot be managed in anything resembling real time. Instructions must be sent and then waited on, measured in days. In 2023, engineers discovered that one of Voyager 1's flight data system computers had developed a problem. It was producing corrupted data, meaningless strings rather than scientific measurements. The problem was not in the instruments themselves, it was in the chip responsible for packaging the data for transmission. Engineers spent months diagnosing the issue remotely, analyzing a machine 24 billion kilometers away using software written in the 1970s. They could not access the affected memory directly. They worked around it, identifying a different section of memory capable of storing the relevant code, rewriting the software to use it, and transmitting the fix one packet at a time across the outer solar system. It worked. Science data began flowing again in April of 2024. A 46-year-old spacecraft, operating on less power than a light bulb, repaired across a distance that takes a signal a full day to cross. The engineers who fixed it were not born when Voyager launched. The probes will not survive indefinitely. Within the next decade, the power remaining will be insufficient to operate any scientific instrument at all. The transmitters will eventually fall below the threshold required to send coherent data. The Deep Space Network will receive noise where it once received measurements and then nothing at all, and the most distant human-made objects in the universe will become silent travelers. Still moving, still following their trajectories, still carrying their golden records through interstellar space with no one left to hear them. What those golden records contain is worth pausing on. Encoded on the surface of a gold-plated copper disc aboard each probe is a collection assembled by a committee chaired by astronomer Carl Sagan. There are greetings in 55 human languages. There are sounds, ocean waves, wind, thunder, a mother's first words to a newborn child, the call of a humpback whale. There is music from dozens of cultures across every inhabited continent. There are 116 images encoded in analog form, photographs of Earth, of human bodies, of mathematical diagrams, of cities and forests and faces. There is a pulsar map identifying the location of the Sun relative to 14 known pulsars, providing any finder with a coordinate system for locating our star. There are instructions for playing the record, etched in diagrams that assume no shared language. The record is addressed to no one in particular because there is no one in particular to address it to. It is a message sent into an unknown that may never answer. In roughly 40,000 years, Voyager 1 will pass within 1.6 light-years of a star in the constellation Camelopardalis. It will not stop there. It will continue through the galaxy, drifting between star systems for billions of years, outlasting the civilization that made it, outlasting perhaps the sun itself, carrying a small gold disc of music and greetings and the sound of the sea into the permanent dark. Voyager is humanity's voice drifting into the galaxy. In science, anomalies are not accidents. They are invitations. When data behaves in ways the current model cannot explain, there are two possibilities. Either the data is wrong, the result of instrument error, observational bias, or measurement noise. Or the model is wrong, incomplete, missing something real that sits just outside what has been accounted for. Science has learned repeatedly and sometimes humiliatingly that anomalies deserve attention. The discovery of Neptune itself came not from a telescope scan, but from an anomaly. The orbit of Uranus, which refused to follow the path that Newtonian gravity predicted. Two mathematicians working independently in the 1840s concluded that the discrepancy was caused by an undiscovered planet beyond Uranus. They calculated where it should be. Astronomers pointed their telescopes at that region of sky. Neptune was there, within 1 degree of the predicted position. The solar system hid a giant planet until mathematics found it first. That lesson has not been forgotten. And right now, in the orbital data of the most distant known objects in the solar system, there is an anomaly. It has been building for years. It has survived multiple attempts to explain it away. It has resisted the corrections applied for observational bias. And the researchers who first formally proposed an explanation for it believe with the careful confidence of people who understand what the numbers are saying, that a large undiscovered planet is orbiting the Sun at a distance so extreme, it has never been directly observed. They call it Planet 9. The anomaly begins in the Kuiper Belt, but it extends beyond it. Among the known populations of distant solar system objects, those with orbits reaching far beyond Neptune into the outer dark, a subset behaves strangely. These are called extreme trans-Neptunian objects, or ETNOs. Their orbits carry them out to hundreds of astronomical units from the Sun, far beyond any planet's direct gravitational influence. At those distances, the mathematical expectation is that their orbital orientations should be essentially random. The direction of their closest approaches to the Sun, the tilt of their orbital planes, the geometry of their trajectories through space, all of it should be distributed evenly across all possible orientations, pointing in no particular preferred direction, arranged with the statistical neutrality of objects that have evolved in isolation. They are not random. They cluster. The closest points of a disproportionate number of these distant orbits point in the same general direction. Their orbital planes share a similar tilt. The clustering is not perfect. It is not the kind of tight alignment that would appear in a simple textbook diagram. But it is statistically significant, and it persists in the data even when corrections are applied for the most obvious source of bias. The fact that surveys can only observe the sky above certain observatories, which means some portions of the sky are better sampled than others. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper analyzing this clustering in detail. Batygin, a theorist, and Brown, the same observational astronomer whose discovery of Eris had helped reclassify Pluto a decade earlier, ran simulations to determine what gravitational influence could produce the orbital patterns they observed. Random chance was statistically disfavored. Known gravitational effects from the giant planets could not account for it. But a single large distant planet, massive enough to gravitationally shepherd these objects across billions of years, produced simulated orbital distributions that match the observed clustering with striking consistency. Their conclusion was measured and specific. A planet with a mass roughly 5 to 10 times that of Earth, orbiting the Sun on a highly elliptical path that carries it between approximately 201,200 astronomical units at its closest and farthest points, inclined at a significant angle to the plane of the solar system, taking somewhere between 10,000 and 20,000 years to complete a single orbit. That is their prediction, not a hope. Not a speculation. A mathematical consequence of the data, derived from the same gravitational physics that predicted Neptune before anyone saw it. But that's not the real problem. The problem is finding it. A planet 5 to 10 times Earth's mass sounds substantial. In the inner solar system, it would be impossible to miss. But Planet 9, if it exists, orbits at distances so extreme that its apparent brightness from Earth would be extraordinarily faint. A planet reflects sunlight at 200 to 1,200 astronomical units. The amount of sunlight reaching that planet is thousands to millions of times less than what reaches Earth. What is reflected back toward us is correspondingly minute. The best current estimates suggest Planet 9, near the far end of its orbit, would appear hundreds of times fainter than the faintest object's current ground-based surveys can reliably detect. Even near its closest approach to the Sun, it would appear as a faint, slow-moving point of light in a sky full of other faint, slow-moving points of light. Slow is the key word. At 200 astronomical units, an object completing a 10,000-year orbit moves across the sky so gradually that distinguishing it from a background star requires comparing images taken months or years apart. Survey telescopes scanning wide fields of sky for fast-moving objects. The traditional technique for finding solar system bodies are optimized for objects much closer in. Planet 9 would require dedicated, deep, wide-field searches using the most powerful imaging systems available. Those searches are underway. Multiple teams have systematically scanned portions of the sky most consistent with Planet 9's predicted orbit. The Subaru telescope in Hawaii has been used for extensive searches. The Dark Energy Survey, originally designed to map distant galaxies and measure the expansion of the universe, has contributed data to the hunt. Researchers have combed through archival observations from legacy surveys, looking for a slow-moving point of light that was present in old data but never identified as a solar system object. Nothing confirmed has been found. The planet, if it exists, remains hidden. Either it is in a portion of the sky not yet deeply surveyed, or it is currently near the far end of its orbit where detection is extraordinarily difficult, or the clustering signal is the product of an observational bias not yet fully understood or corrected for, and no planet exists at all. It gets worse. The debate within the astronomical community is genuine and unresolved. A significant number of researchers have argued that the clustering of distant Kuiper Belt objects is an artifact, a statistical illusion produced by the specific observation strategies used to find those objects in the first place. If surveys consistently target certain regions of sky more than others, the objects found in those surveys will have orbital geometries pointing preferentially toward those regions. Several analyses, using expanded samples and more careful bias corrections, have argued the statistical significance of the clustering weakens considerably when these factors are properly accounted for. The signal in those analyses is not compelling enough to require a planet as an explanation. Badajian and Brown have responded to these criticisms with updated analyses and additional lines of evidence. They have pointed to the perpendicular population, a group of Kuiper Belt objects whose orbits are tilted nearly 90 degrees relative to the plane of the solar system, a configuration that the simulations predict as a natural consequence of gravitational interaction with Planet 9's inclined orbit. They have pointed to objects like Sedna, a dwarf planet discovered by Brown in 2003, whose orbit keeps it perpetually far from Neptune, at distances the known planets cannot explain through any combination of standard gravitational interactions. Sedna's existence was one of the earliest hints that something unusual occupies the outer solar system. Whether that something is Planet 9 specifically or some other process from the solar system's early history remains the core of the dispute. What both sides agree on is this: the outer solar system is poorly mapped. The surveys conducted to date have covered only a fraction of the sky to the depth required to find an object as faint as Planet 9. The Vera C. Rubin Observatory, now in its commissioning phase in Chile, is expected to change that when its full survey program begins. The Legacy Survey of Space and Time, a 10-year imaging program that will photograph the entire visible sky repeatedly, building up sensitivity through stacked observations. We'll probe the sky more deeply and more uniformly than any previous survey. If Planet 9 exists anywhere within the range of predicted positions and at the predicted brightness, there is a reasonable chance the Rubin Observatory will find it within the survey's operational lifetime. And this changes everything, because the implications of finding Planet 9 are not limited to adding a 9th entry to the planetary count. A planet of 5 to 10 Earth masses orbiting at those distances would demand a complete revision of our understanding of how this solar system formed and what happened to it in the billions of years since. Where did it come from? Was it scattered outward from the inner solar system during the period of giant planet migration? Did it form in the outer disk and never migrate inward? Was it captured from a passing star system? Each origin story carries different consequences for how the solar system assembled, how the Kuiper Belt was populated, and what other undiscovered structures might exist in the deep outer solar system. The possibility also carries a more unsettling implication. If a planet 10 times Earth's mass has remained undetected this long, orbiting within our own solar system, it raises a quiet question about how well we actually know the place we live. Every generation has assumed the planetary inventory was complete. Every generation has been shown a gap. The gap this time is not a reclassification or a population of small frozen objects. It is a potential world, vast, cold, dark, and patient, circling the sun on a path so wide that a single orbit spans longer than human civilization has existed. Whether it is found or not, the hunt itself is a statement about the limits of what we know. The solar system is not fully mapped. The outermost regions remain uncertain territory. And somewhere in the long arc of darkness between the Kuiper Belt and the Oort Cloud, something may be moving that we have not yet named. Our solar system may still be hiding a giant planet. Watch a comet, not through a telescope, not in a photograph. Stand outside on a clear night when one is visible and watch it with your own eyes. The bright nucleus, the tail stretching away from the sun across degrees of sky, the slow, silent movement against the stars over successive nights as it falls toward perihelion, and then swings back outward. It looks ancient. It feels ancient. There is something in the human nervous system that responds to a comet differently than to a planet or a star. A recognition, perhaps instinctive, that this is a traveler. Something passing through rather than something that belongs here. Every culture that recorded the night sky noted comets with particular attention. Some with fear, some with wonder, all with the correct intuition that a comet is not a permanent fixture of the sky but an arrival from somewhere else. Science eventually confirmed that intuition and then extended it into territory the original observers could not have imagined. Comets come from the edge. Not the edge most people picture when they hear that word. Not the orbit of Pluto, not the scattered remnants of the Kuiper Belt. The comets with the longest orbital periods, the ones that take thousands or tens of thousands of years to complete a single journey around the sun, come from a region so remote that it sits at the outermost boundary of anything that could reasonably be called the solar system. A place where the sun is merely the brightest star in a sky full of stars. A place where the temperature has hovered near absolute zero for billions of years. A place where objects orbit so slowly on paths so vast that they have completed only a handful of circuits around the sun since the solar system formed. That place has a name, the Oort Cloud. And understanding it means confronting a scale of distance that makes everything discussed so far, the Kuiper Belt, the heliosphere, the heliopause, feel like the neighborhood immediately surrounding your front door. The idea was formalized in 1950 by Dutch astronomer John Oort, though earlier researchers had pointed towards similar conclusions. Oort noticed something systematic about long-period comets, those with orbital periods exceeding 200 years. When he analyzed their orbital parameters, he found that an unusual number of them appeared to arrive from distances of roughly 50,000 astronomical units or more. They were not coming from the Kuiper Belt. They were not coming from any known population of objects in the ecliptic plane. They were arriving from all directions, above, below, and across the plane of the solar system, with a roughly spherical distribution that suggested their source was not a ring or a disk, but a shell. A vast, three-dimensional cloud of objects surrounding the sun at enormous distance, sending comets inward occasionally when something disturbed their distant orbits. Oort proposed that such a cloud existed. He could not observe it directly. No one has since. The individual objects within the Oort cloud are too small, too dark, and too distant to be detected by any telescope currently operational. What exists is inferred, deduced from the comets that fall inward and the orbital mechanics that must have produced them. The Oort cloud is science working backwards from the evidence, reconstructing a structure from its consequences the way a detective reconstructs an event from the traces left behind. What the inference produces is staggering. The Oort cloud is thought to begin at somewhere between 2,000 and 5,000 astronomical units from the Sun, already far beyond anything the Voyager probes have reached, at distances that would take these spacecraft tens of thousands of years to cover at their current speed. The inner region of the cloud, sometimes called the Hills Cloud or inner Oort Cloud, is thought to be a flattened or toroidal structure, denser than the outer regions, less directly accessible to the gravitational perturbations that occasionally disturb it. The outer Oort cloud extends from perhaps 20,000 astronomical units to somewhere between 50,000 and 100,000 astronomical units, or possibly farther. At its outer limit, the Sun's gravitational hold on individual objects is so tenuous that passing stars, the gravitational tide of the Milky Way galaxy itself, and even individual molecular clouds can measurably alter the orbits of Oort cloud objects. The outer edge of the Oort cloud, at 100,000 astronomical units, corresponds to approximately 1.6 light-years from the Sun. Proxima Centauri, our nearest stellar neighbor, lies at roughly 4.2 light-years. The Oort cloud does not reach Proxima Centauri, but it reaches more than a third of the way there. The solar system, defined by the reach of solar gravity, extends deep into the space between stars, not merely brushing the outskirts of interstellar space, but penetrating it, overlapping with it, dissolving into it across a gradient that has no clean line. But that's not the real problem. The population of objects within the Oort cloud is estimated in the trillions, not billions. Trillions of individual icy bodies, ranging from small cometary nuclei a few kilometers across to larger objects potentially rivaling Kuiper Belt dwarf planets in size. Most will never move. They will orbit in the cold and dark for the remaining lifetime of the solar system, without ever being disturbed enough to fall inward toward the Sun. They formed in the inner solar system, in the same region where the giant planets assembled, and were flung outward by gravitational interactions during the chaotic early period of planetary migration. They carry within their composition the chemistry of the young inner solar system, preserved intact by the cold of their distant orbits, unchanged across billions of years. Every long-period comet that falls through the inner solar system is carrying a sample of that ancient chemistry back into the neighborhood where it formed. The total mass of the Oort Cloud is unknown. Estimates vary enormously from a few Earth masses to considerably more, because the population can only be inferred statistically from the rate and distribution of comets arriving in the inner solar system. The uncertainty is not a gap that better telescopes will soon close. It is a fundamental limitation imposed by the physics of detection at those distances. The Oort Cloud may remain unresolvable into individual objects for the foreseeable future of human technology. It gets worse. The Oort Cloud is not stable. Its outer regions are under constant, low-level assault from the gravitational environment of the galaxy. The most significant perturber is passing stars. The Sun moves through the galaxy at roughly 220 kilometers per second relative to the galactic center, and over millions of years, other stars occasionally pass through or near the outer solar system. Not collisions, not close encounters in any human sense of the phrase, but passages within a light year or two, distances enormous by everyday measure but close enough, given the scale of the Oort Cloud, to gravitationally nudge thousands of objects out of their stable orbits. When a passing star pulls on the outer Oort Cloud, it sends a rain of comets falling inward toward the Sun. Some arrive in the inner solar system over the following millions of years as long-period comets. Some are scattered entirely out of the solar system, lost to interstellar space forever. Some fall into the giant planets and are captured or destroyed. The cometary showers associated with close stellar passages are thought to have influenced the impact history of the inner solar system, including, potentially, the bombardment history of the early Earth. The passing of distant stars tracing paths through the outer solar system without a single human observation of the event may have shaped the conditions that allowed life to develop here. The Milky Way's galactic tide provides a gentler but continuous perturbation. The galaxy's gravitational field is not uniform. It varies with distance from the galactic center, from the galactic plane, and with the distribution of mass in the spiral arms. As the solar system orbits the galaxy, it experiences these variations as a slowly changing tidal force. Over millions of years, the galactic tide deforms the outer Oort Cloud, compressing and stretching it, nudging the most loosely bound objects into new orbits. The boundary between what belongs to the solar system and what belongs to the galaxy is not simply drawn in space. It is drawn in time. The outer Oort Cloud is perpetually being reshaped by galactic forces that operate on timescales no human institution has ever existed long enough to witness. And this changes everything, because the Oort Cloud is not merely an outer boundary, it is a record, a physical archive of the solar system's entire history of galactic motion, stellar neighbors, and gravitational disruptions stretching back to the earliest epochs of solar system formation. The distribution of orbital parameters across the Oort Cloud population encodes which stars have passed close to the solar system, when those passages occurred, and how violently they disturb the outer edges of solar gravity's reach. Reading that archive directly, mapping the Oort Cloud with sufficient resolution to reconstruct the solar system's stellar neighborhood over billions of years, remains beyond current capability. But it is not beyond theoretical modeling. Astronomers have used the orbital properties of observed long-period comets to constrain the history of nearby stellar passages, inferring encounters from the signatures they left behind in the comet population that survived them. There is a deeper implication here that the scale tends to obscure. The Oort Cloud means that every other star system in the galaxy, every system that has formed in the same way as ours, likely possesses its own equivalent structure. A vast spherical shell of frozen ancient material surrounding each star, extending far into the interstellar gaps. As stars pass within a light year or two of each other over galactic timescales, their Oort clouds would overlap. Material could theoretically transfer between star systems. Cometary bodies from one stellar neighborhood dragged into the gravitational dominion of another. The interstellar space between stars may not be as sterile and empty as it appears. It may be threaded occasionally by the outer fringes of Oort clouds drifting close enough to exchange objects across the void. Whether this actually happens at meaningful rates is uncertain. Demonstrated interstellar objects have already been observed passing through the solar system. Oumuamua in 2017 and Borisov in 2019 both traveled through the inner solar system on hyperbolic trajectories consistent with origins outside the solar system. Neither object's precise origin has been definitively established. Both serve as confirmation that material does move between star systems. The galaxy is not divided into perfectly isolated stellar domains. The boundaries are porous. The Oort cloud, then, is not simply the outermost layer of the solar system. It is the place where the solar system blurs into the galaxy, where the sun's gravitational ownership of objects becomes statistical rather than certain, where the distinction between our solar system and the surrounding interstellar environment becomes a matter of probability, not precision. Objects in the inner Oort cloud almost certainly belong to the solar system for the remainder of its lifetime. Objects in the outer Oort cloud might belong to it, or might be lost to a passing star in the next 100 million years, or might already be on trajectories that will carry them away. The edge is not a line. It is a gradient. A slow, cold, ancient dissolution of solar gravity into galactic gravity, measured not in kilometers but in light years, and operating on timescales that reduce the entire span of human civilization to an unmeasurable instant. Every long-period comet that has ever crossed the inner solar system, every comet that ancient astronomers watched, recorded, feared, and named, began its journey in that cloud. It fell from the dark at the edge of everything, inward across 50,000 or 80,000 astronomical units of nothing, accelerating as the sun's gravity reached out and pulled it closer, approaching perihelion in a blaze of sublimating ice before swinging back out to silence. Each one is a messenger from the true edge, a fragment of the boundary itself, falling inward just long enough to be seen before returning to the place where the solar system ends and the galaxy begins. The solar system may extend halfway to another star. Every boundary humanity has ever drawn has been a decision, a choice about where one thing ends and another begins. Coastlines are drawn at the waterline, though the sea advances and retreats with every tide. National borders are drawn across mountains and rivers that predate the nations themselves. The edge of a city is drawn where a municipality decides, not where the urban fabric actually stops. Boundaries are useful. They are also, in almost every case, approximations. Convenient fictions that impose definition on phenomena that resist it. The edge of the solar system is not a decision. Nobody drew it. Nobody agreed on it at a conference or encoded it in a resolution. It exists, or it fails to exist, entirely on its own terms. And its own terms are far more complicated than any diagram, any textbook definition, or any intuitive concept of boundary has ever suggested. To locate the true edge of the solar system, you have to ask a precise question. Not where the planets stop, not where the solar wind stops, not even where the last identifiable icy object orbits. The precise question is this: at what distance from the Sun does the Sun's gravitational influence lose dominance over competing gravitational forces? Where does the Sun's hold on objects become weaker than the pull of everything else? The galaxy, the stars, the distributed mass of the Milky Way itself. That question has a framework for an answer. It is called the Hill sphere. The Hill sphere, named after American astronomer George William Hill, describes the region around a gravitational body within which that body can maintain stable gravitational control over smaller orbiting objects in the presence of a larger competing gravitational influence. Every planet has a Hill sphere relative to the Sun, the region within which a moon can maintain a stable orbit around the planet rather than being captured by solar gravity. The Earth's Hill sphere extends to roughly 1.5 million kilometers, which is why the moon, orbiting at an average of 384,000 kilometers, remains securely bound to Earth rather than drifting away into a solar orbit. Jupiter's Hill sphere is vastly larger, which is why Jupiter holds dozens of moons, including some on highly irregular distant orbits. The Sun has its own Hill sphere, its own region of dominant gravitational control relative to the competing gravitational influence of the Milky Way galaxy. The galaxy's gravitational pull, not from any single nearby star, but from the combined mass of hundreds of billions of stars, the dark matter distributed throughout the galactic structure, and the accumulated pull of everything the galaxy contains, acts as the competing force that ultimately defines where the Sun's dominance ends. The Sun's Hill sphere extends to roughly 1 to 2 light-years. At that distance, the galaxy's tidal force becomes comparable to the Sun's gravitational pull on loosely bound objects. Objects orbiting within that boundary can maintain stable long-term orbits around the Sun. Objects beyond it are gravitationally vulnerable, subject to perturbation, capture, or gradual drift away from the solar system over cosmological timescales. This is not a sharp wall, it is a threshold, a region of transition where the balance between solar gravity and galactic gravity tips from one side to the other, and where the concept of belonging to the solar system becomes probabilistic rather than definitive. The outer Oort Cloud sits close to this boundary. Some of its constituent objects may already be near or beyond the limits of the Sun's long-term gravitational retention. They orbit, but they orbit uncertainly. Held for now, potentially lost over the next billion years if the right perturbation arrives at the right moment. The outermost solar system is not a stable archive. It is a slow leak. But that's not the real problem. The Hill sphere defines a theoretical limit under idealized conditions. A sun and a galaxy, with no other complicating forces. The actual outer solar system is not idealized. It is threaded by forces that operate across multiple scales simultaneously, each one capable of redrawing the effective boundary on different timescales, in different directions, and with different consequences. The galactic tide is the most persistent. As the solar system orbits the Milky Way, completing a circuit roughly every 225 million years, it experiences variations in the galaxy's gravitational field that arise from its changing distance from the galactic center and its oscillation above and below the galactic plane. These variations produce a tidal force, not the dramatic tidal forces of moons and planets, but a slow, vast gravitational gradient that acts differently on objects at different distances from the Sun. In the outer Oort cloud, this tidal force is strong enough to gradually alter orbital inclinations and eccentricities over millions of years, nudging objects onto paths that eventually bring them inward as long-period comets. The galactic tide is not a catastrophic event. It is a perpetual, gentle erosion of the outer solar system's stability, operating continuously across timescales that make planetary formation look brief. Passing stars complicate the picture further. The Sun is not stationary relative to nearby stars. It moves through the galaxy, and other stars move through the galaxy, and occasionally those paths bring another star within a light year or two of the solar system. At those distances, the gravitational influence of the passing star on the outer Oort cloud is measurable. It perturbs orbits. It scatters some objects deeper into the solar system, triggering comet showers that can last millions of years. It pulls other objects out of the solar system entirely, liberating them from solar gravity and releasing them into the interstellar medium as unbound bodies. The solar system's outer edge is not merely eroded by the galaxy from the outside. It is punctured repeatedly by the gravitational reach of individual stars passing through what we call our territory. It gets worse. These forces do not operate in isolation. The galactic tide, passing stars, and the internal dynamics of the Oort cloud interact with each other in ways that amplify their individual effects. A star passage that would, in isolation, send only a modest rain of comets inward may do considerably more if it acts in concert with a phase of the galactic tide that has already destabilized a large population of outer Oort cloud objects. The boundary of the solar system, under the influence of these combined forces, is not fixed in space. It flexes, it breathes. It contracts slightly and expands slightly over millions of years as the solar neighborhood changes. It is not a static feature of the cosmos. It is a dynamic one, shaped in real time by a galactic environment that the Sun moves through continuously and cannot escape. The interstellar medium adds another layer. The thin gas and dust of interstellar space exerts a small but non-zero drag on the outermost objects of the solar system over geological timescales. More significantly, the density of the interstellar medium varies as the solar system passes through different regions of the galaxy. Denser in the spiral arms, thinner in the gaps between them. The solar system entered the local interstellar cloud, a region of somewhat elevated interstellar gas density, roughly 60,000 to 100,000 years ago. The heliosphere's shape and extent change as the interstellar medium's properties change. The boundary defined by the heliopause shifts. What lies just outside the solar system is not a fixed, neutral void. It is a varying environment, and the solar system responds to those variations continuously. And this changes everything. Because if the boundary is dynamic, if it flexes with stellar passages and galactic tides and interstellar medium variations, then the question of where the solar system ends cannot be answered with a single number. It can only be answered with a range, a probability, a description of the forces at work and the timescales on which they operate. The solar system does not have an edge in the sense that a table has an edge. It has a gradient, a region of space where solar gravity shades into galactic gravity, where the Sun's influence becomes one voice among many rather than the only voice, where the ancient frozen records of solar system formation become cosmologically untethered. This is difficult to accept intuitively. The human mind wants borders. It wants the solar system to be a thing with the surface. Something you could cross, something you could photograph from the outside, something that separates here from there in a way that is visible and definitive. But the solar system is not that kind of thing. It is a gravitational sphere of influence embedded in a galaxy, shaped by forces that extend in every direction simultaneously, gradually losing coherence at its outermost edges in a dissolution that has no single moment and no single location. What that dissolution means philosophically is something worth holding for a moment before releasing it. The solar system, the entity that contains the sun, all the planets, all the moons, all the asteroids, all the frozen relics of the Kuiper Belt, the heliosphere, the hypothetical planet 9, the vast and ancient Oort Cloud, and everything else gravitationally bound to our star, is itself just a feature of a larger structure. The Milky Way contains at minimum 200 billion stars, each one potentially surrounded by its own system of planets, moons, comets, and distant icy clouds. Each one with its own Hill sphere, each one dissolving at its edges into the same galactic environment. The solar system is one gravitational island in an ocean of gravitational islands, and the ocean does not care about the island's boundaries. From the outermost edge of the Oort Cloud, if you could somehow position yourself there and look back, the sun would be one star among many. Brighter than its neighbors from that vantage point, still the dominant gravitational presence within the sphere of space surrounding it, but visually indistinguishable to any observer without prior knowledge of which point of light to study. Earth would be invisible. Every planet would be invisible. The entire history of human civilization, every city, every ocean crossed, every war fought, every piece of music ever composed, would be contained within a volume of space smaller than could be resolved at that distance. The solar system, from its own outermost edge, has already become a star. The Milky Way does not acknowledge the solar system's edge. It simply continues in all directions, in the same ancient indifference it has maintained for the 13 billion years it has existed. The stars keep passing, the tides keep pulling, the interstellar medium keeps flowing, and the outer boundary of the solar system keeps shifting, slowly in response, contracting here, stretching there, losing objects over millions of years and occasionally gathering others that wander within reach, breathing with a rhythm so slow that the entire span of human existence registers as less than a single breath. The edge of the solar system is not a destination, it is a condition, a state of gravitational ambiguity that exists wherever the sun's authority fades and the galaxy's begins. Not abruptly, not violently, but in the way that all certainties eventually fade when confronted with something larger than themselves. We live inside that authority, on a planet that has never come close to its boundary, in a civilization that has only just sent its first tentative messengers toward the inner edges of the transition zone. The outermost solar system remains unmapped, largely theoretical, and almost certainly stranger than current models suggest. It always has been. The edge of the solar system is where the galaxy begins.